Hi, welcome back everybody. In this video we will complete our derivation of fixation probability of an adaptive mutation which confers a benefit to the mutant that has arisen in the population. So, in the last video we had made quite a bit of progress towards deriving this expression through some cumbersome but simple math. The bookkeeping was a bit ugly, but the math itself was not very hard. And at the end of this exercise, we had come up with the expression for fixation probability of a beneficial mutation as the following expression: 1 divided by 1 plus gamma 1 plus gamma 1 gamma 2 going all the way up to gamma 1 gamma 2 gamma n minus 1. So, one thing you should realize, so this is the fixation probability for a mutation. Or this is also can be rewritten as probability that system currently at I equal to 1 will reach n. That the beneficial mutant that has arisen in the population will be able to outcompete the ancestor genotype that is present in the population, of which there are n minus 1 individuals. It will be able to outcompete all of them and fix in the population. One thing that this expression immediately tells us, that this expression is always less than 1, because the numerator is 1 and the denominator is 1 plus something, if I call all of this something. So, fixation probability x1, it seems, is equal to this, which is always less than 1. So, that means there is immediately a lesson to be learned, that we have been discussing natural selection, and what natural selection tells us is that if any beneficial mutation comes up in the population, it will certainly reach fixation, because it is going to get selected by, it is going to get selected for, and its progeny will be able to outcompete the progeny of the ancestral genotype that is already present in the population. This expression, without working out the exact expression, immediately tells us that that is not going to be the case. X1 is less than 1. However, this obviously does not tell us by how much how small is this quantity as compared to 1. Is it 0.99 or is it 0.01? And that is our goal in this lecture, that we want to arrive at the precise expression which helps us quantify this fixation probability. So, for that, obviously all we need is these ratios gamma I, where gamma I was beta I upon alpha I. And if you recall, beta I upon alpha I was simply this ratio, that if we are at stage I and from there in one more step we can go to I plus 1, this probability was alpha I, or we can go to I minus 1, this probability was beta I, and we simply need the ratio of these two. Of course, the other possible outcome here is 1 minus alpha I minus beta I, and the two ends of this system are I equals n and I equals 0. So, we need an expression for gamma I. If we get that, we should be able to arrive at an expression for x1, and that is simply equal to beta I upon alpha I. Now, go back to the, let's take our minds back to the discussion of Moran process, where we discussed beta I and alpha I. This is simply the probability beta I that system transitions from I to I minus 1, and alpha I is simply the probability that system transitions from I to I plus 1. Transition from I to I minus 1 can only happen if the birth event is of an A type individual and death event is of a B type individual, the mutant. This is the mutant that we have been discussing all along, and that is why the number of mutants in the population is going to reduce by 1. Alternatively, I to I plus 1 transition will only take place if birth event is of B type and death event is of A type, and hence because of this the number of blue type individuals in the population increases by 1 and goes from I to I plus 1. So, let us write down the expressions of these terms. The probability that birth of A type individual is simply going to be the combined fitness of all the A type individuals divided by total fitness of all individuals in the population. So, the birth term probability is simply going to be n minus I times R A divided by n minus I times R A plus I times R B. The probability of death of a mutant type is simply going to be proportional to the number of mutant individuals that exist in the population at the time, which is simply going to be I upon n. So, these two multiplied together give me an expression for the numerator here is simply this. The denominator we can write that by using the same logic, that now we are saying that birth has to be of a B type individual whose probability is going to be the combined fitness of all B type individuals divided by total fitness of the entire population, in which case that is going to be I times R B divided by n minus I times R A plus I times R B. And that has to be coupled with the fact that a death has to be of a individual, which is simply going to be proportional to the number of A type individuals in the population, which will be n minus I upon n. And this gives me the complete expression that I need for beta I divided by alpha I, which is gamma I. We can simplify this a little bit if you carefully look at this, and we can see that this n and this n can cancel each other. So, this goes. We can see that this I and this I can cancel each other. So, this goes. We can also see that this n minus 1 can be cancelled with this n minus 1. So, all of this goes, and we should be able to see that the denominator here was total fitness of the population, and the denominator here is also the total fitness of the population. These two are identical. So, this denominator cancels with this denominator, and eventually we are left with a very simple expression for gamma I, which is equal to R A divided by R B. And somewhat fortuitously for us, this value of gamma I, so this is gamma I, this value of gamma I is not dependent on I. Whether I is 1 or 2 or 3 or it does not matter, gamma I for every value of I, the value of gamma I is a constant which is simply R A by R B. So, you should note here that R A is the fitness of ancestor genotype and R B is the fitness of the mutant genotype. Because we started this discussion with the assumption that the mutant we are going to be discussing will be an adaptive mutation, a adaptive mutant which has come up and is actually has a higher fitness than that of the ancestral genotype. We know that RB by definition is greater than RA. As a result of this, gamma I is actually less than 1. So, now pieces are falling together. We have all gamma i's, whether be it gamma 1, gamma 2 have the same value RA by RB. So, all I have to do now is go back to the expression for x1 and plug those in. When I do that, so x1 is simply equal to 1 divided by 1 plus gamma 1 plus gamma 1 gamma 2 plus gamma 1 gamma 2 gamma 3 going all the way to gamma 1 gamma 2 gamma n minus 1. So, in the denominator there are n terms starting with 1 ending with gamma 1 to gamma n minus 1 all multiplied together, and each gamma I is simply equal to R A divided by R B, and we can write this as simply as 1 upon R, where R is the relative fitness of B as compared to A. Another way to see this is I can write this ratio as 1 upon RB by RA, and this ratio of RB by RA is what I am calling R. So, then this x1 becomes 1 divided by 1 plus 1 by R plus 1 by R times 1 by R plus 1 by R times 1 by R times 1 by R going all the way up to 1 by R times 1 by R times 1 by R n minus 1 term, n minus 1 times. I hope everybody is able to see that the denominator is a geometric progression. Geometric progression with A as the first term, of the geometric progression in our case is just this, which is 1, and the common ratio between successive terms is simply equal to 1 upon R. So, this summation applying the formula of geometric progression, and there are in this entire expansion, in this entire series of geometric progression, there are a total of n terms. First term as 1, common ratio as 1 by R, and there are n terms. So, that's simply substituting for the formula of geometric progression, I get this expression as 1 common ratio to the power number of terms minus 1 divided by common ratio minus 1. That is just the summation formula that I have applied in the denominator here for a geometric progression. Please look it up in any reference book if you are not familiar with geometric progression or have forgotten the formula for the sum. So, this goes in the numerator, and then x1 comes out to be 1 upon r minus 1 divided by 1 upon r raised to power n minus 1. Remember that r was simply equal to, it is a common ratio. Let us take a look what we called r. R was defined as Rb upon Ra. So, this is Rb upon Ra, and n is the population size. Since Rb is greater than Ra, since this is the case, what that means is that R is greater than 1, because the numerator is Rb, which is a bigger number than Ra. So, that is greater than 1. So, what that means is that 1 by r is a number which is less than 1, and 1 by r to the power n, n is the population size, so another positive number. So, this ratio, if I were to highlight this here, this ratio is less than 1, and this ratio also is less than 1. So, and when I subtract 1 from both, it turns out that numerator will be negative and denominator will be negative too, but that's okay. But I can write this as, to make both positive, I can write this as x1 as 1 minus 1 upon r and denominator as 1 minus 1 upon r to the power n. And I can do that because I have multiplied basically numerator and denominator by minus 1. So, I have switched the terms. Now, we are almost there, except for the fact that we can simplify this a little bit more. 1 by r is a number which is less than 1, because r is greater than 1, and n is a number which is very large for a microbial population, let us say is of the order of 10 to the power 6. That is at the very least, it can be much bigger than that also. So, I have a number which is less than 1 and I raised to the power it by 10 to the power 6. This number will be very close to 0. It's, for example, if you imagine that if I have 0.9, 0.9 square is only 0.81, which is less than 0.9 to the power 1, and if I do 0.9 to the power 3, that is going to be less than 0.1, and every subsequent time I multiply it with 0.9, the number keeps on decreasing, and here I am multiplying a number which is less than 1 10 to the power 6 times. So, this is going to be a really small number and I am just going to ignore it. This number is a really small number. So, x1 is approximately equal to 1 upon 1 minus r. Okay, we are almost there. So, x1 is approximately equal to 1 minus 1 upon r, where r is equal to rb minus, not minus, rb divided by ra. So, if I substitute that here, x1 is equal to 1 minus 1 upon rb by ra. This can be written as 1 minus ra divided by rb, which can be written as RB minus RA divided by RB. Now, without any loss of generality, let's normalize everything. Let's normalize everything with respect to RA, and let's assume that RA is equal to 1 and RB is equal to 1 plus S, where S is the selection coefficient associated with the beneficial mutation that arose when a blue individual was born, when a existing black individual divided and a progeny had acquired a mutation. So, we are saying that the fitness of this guy is 1 and the fitness of this guy is 1 plus S. So, this is 1 plus S minus 1 divided by 1 plus S. These 1's cancel and we get S upon 1 plus S. This is the fixation probability associated with a beneficial mutation. So, we have finally arrived at the fixation probability of a beneficial mutation, and it simply says that x1 is equal to S upon 1 plus S. So, now what we are saying is that if we have a population size n and we have a beneficial mutant that arises in the population, it is present at 1. The probability that this beneficial mutation will be able to outcompete the existing n minus individuals of lower fitness and reach fixation, this probability x1 is simply equal to S upon 1 plus S. S is the relative advantage that it enjoys over the ancestral population. So, let us plug in some numbers. In the E. coli evolution experiment, we saw what sort of effect did those 5 beneficial mutations had. We saw that after occurrence of these 5 beneficial mutations, fitness had increased by 35%. So, by 0.35. That means each mutation conferred a benefit of about 0.07, that was the S. Let us assume that each one of those conferred equal benefit. So, the S associated with each of these mutations was 0.07, which means for a mutation like that, the x1, this is approximate, is going to be 0.07 divided by 1 plus 0.07, which is just equal to 0.07 divided by 1.07, which is approximately equal to 0.07. Because S is a small number usually as compared to 1, because as you can see that a single beneficial mutation only provides a benefit about 5-6%. So, S will be typically 0.04, 0.05 and so on and so forth, whereas 1 is like several times bigger than that. What is usually safe to assume that x1 is almost equal to S, which means that when a beneficial mutation occurs, it only has a chance which is proportional to the fractional benefit, the relative advantage that it provides of reaching fixation. All other times it is going to go extinct. So, if we are talking of a beneficial mutation that confers an advantage of 5%, what that means is that if this mutation occurred 20 times in the population, 19 times it will go extinct and only 1 time it will go to fixation. So, while in other words, if all beneficial mutations were providing this amount of benefit, in other words, 20 beneficial mutations need to occur in a population for one of them to go to fixation. Still we see this is much better as compared to what we saw with neutral mutations, where we saw that 10 to the power 6 mutations needed to happen for one of them to go to fixation. Almost, so a million mutations needed to happen for one of them to reach fixation under neutral evolution. This is adaptive evolution, where the mutation that is occurring provides fitness advantage to the population, and hence you need far fewer mutations to happen before one of them has a chance to outcompete and reach fixation. But even then, we are seeing that for typical values of the selection coefficients that beneficial mutations provide, actually most of the mutation and overwhelming majority of the mutations still just go extinct because of the action of drift, and only a very small fraction are able to reach fixation. In other words, we can also think of this in the following way, that natural selection, when a mutation happens, when a mutation first happens, the system is right here. The system is right here, and at this time there is a tussle between what is going to happen to this mutation between natural selection and drift. Natural selection's effect will be that it is going to increase the mutation, it is going to select for the more fitter type of individual, which is going to take it to fixation and towards N. So, this is natural selection. Drift does not really care. Drift does not care where the system goes. It is happy to take the system in this direction or in this direction. Drift does not really care one way or the other. Despite the action, so this is the action of drift or chance events. Despite the action of natural selection and drift being associated like this, what we are seeing that for a beneficial mutation that confers a benefit of, let us say, 5%, the numbers tell us that actually a mutation is going to end up at fixation. For every mutation that ends up here, there are going to be 19 mutations that end up going extinct. And you might wonder as to why that is happening despite natural selection acting in one particular direction and drift not caring which direction it acts on. That is because of the location of this point, because starting a game from this point, the action of drift, even if 50% of the times drift takes a step in this direction, as soon as you reach this particular point, the game is over, because the one individual carrying that beneficial mutation is gone. So, even if it was 50-50 chance, the 50% that took a step in this direction are immediately removed from the population. For the 50% that took a step in this direction, they are still vulnerable, because 50% of them will take another step in this direction and 50% of them will take another step in this direction, and then they will go extinct. So, when numbers are small, drift and chance events do these things, which lead to a surprising outcome that you need 20 beneficial mutations with S equal to 0.05 to happen, so that one goes to fixation, one fixes, and the other 19 just go extinct. And we will continue this discussion in the next video, where we do some more analysis on a system such as this.